Math Unit 2 paper. Alright, so let's get started. Module 1. It says, a curve is defined parametrically as x is equal to t over 1 plus t, and y is given by t cubed over 1 plus t. Determine the gradient at the point a half a half. To determine the gradient at this point, we are going to need to find dy by dx. So let's go ahead and find dy by dx. So first, to find dy by dx, we know that dy by dx is dy by dt times dt dx. So let's find dy by dt. dy by dt is, we can use quotient rule to find dy by dt. So dy by dt is start with the bottom, then we multiply it by the differential of the top, and the differential of the top is 3t squared minus the top, which is t, times the differential of the bottom, which is 1 plus t, over the bottom square. So we start with the bottom, differentiate the top, 3t squared minus the top, and the top is t cubed, minus the top. Start with the bottom times the differential of the top minus the top times the differential of the bottom. The differential of 1 plus t is just 1. So it's just minus t cubed over the bottom square, which is 1 plus t all square. We can go ahead and simplify this to be that dy by dt is, if you're to expand this, you get 3t squared plus 3t cubed. 3t cubed minus t cubed is 2t cubed. And then you have this one times 3t squared, so it's 2t cubed plus 3t squared over 1 plus t all squared. So that's dy by dt. So now let's go ahead and find dx dt. So dx dt, that means we're differentiating the function now. We're differentiating x with respect to t. We start with the bottom, which is 1 plus t, multiplied by the differential of the top. The differential of the top is 1, minus the top, which is t, times the differential of the bottom. The bottom is just differentiate 1 plus t, let's get 1 over the bottom square. And so if you work out 1 plus t minus t, 1 plus t minus t, the t minus t cancel. So you just get 1 over 1 plus t all square. So now we may proceed to go ahead and find dy by dx. So dy by dx, as we know, dy by dx is equal to dy by dt times dt dx. So it's going to be equal to this, which is 2t cubed plus 3t squared over 1 plus t all square. And that is being multiplied by dt dx. dt dx is going to be 1 plus t squared over 1. After we do that now, we're going to observe that 1 plus t squared cancels to 1 plus t squared. And so dy by dx is just this. Now we need to find the value of t when x is a half and y is a half, so that we can plug in that value for t. So let's go ahead and find that when x is a half, we get that t over 1 plus t is equal to half. So we need to find what t is. So we cross multiply and we get 1 plus t. 1 plus t is equal to 1 plus t, not 1 plus 2t. 1 plus t is equal to 2 times t is 2t. And so we bring over this t here. And so we're going to get t equal 1. T equal 1. Let's check it. 1 over 1 plus 1 is a half. Yeah, so t equal 1. So t equal 1. And so now we're able to find dy by dx at a half. So dy by dx is going to be equal to, or we can rather say, the gradient at that point. All right. So the gradient at the point a half, a half, so the gradient at the point half, half is equal to, plug in when t equal 1, you get 2 times 1 cubed, which is 2 times 1, plus 3 times 1 square, which is plus 3 times 1. And so the gradient at this point is equal to 5. Nice and easy. That's the first part of this question. The gradient is 5. Continuing right along. It says, hence, determine the x and y intercepts of the tangent that touches the curve at the point a half, a half. Determine the x and y intercepts. So first we're going to find the equation of the tangent. The equation of the tangent is going to be given by y minus yp. So it's y minus a half is equal to the gradient of the tangent, which we find is 5 into x minus a half. All right, so let me see. This is the equation of the tangent. This is the equation of the tangent, so I'm going to rewrite this now as y is equal to 5x. Then I have the 5 times minus a half is minus 5 over 2. And I add a half to minus 5 over 2, so 0.5 plus minus 5 over 2. And I get minus 2. So this is the equation of the tangent. The equation of the tangent is 5x minus 2. That's the equation of the tangent. Now let's look what the question said now. It said, hence determine the x and y intercepts of the tangent that touches the curve at the point a half, half. Determine the x and y intercepts of the tangent that touches the curve. So when it's talking about x and y intercepts, so I don't know how this curve look. I'm just going to draw some random curve. So we have some random curve. Let's say the curve looks something like this. And we have some tangent looking something like this. And what did they say they want? They say they want determine the x and y intercepts of the tangent that touches the curve at x and y intercepts, meaning where it crosses the axis. So this is what they want. They want this here and this here. So they want the x and y axis intercepts. So now we know that the x-intercept, so the x-intercept occurs when y is 0. So if you were to set y to be 0, you get that x-intercept. Let's write it down. So the x-intercept occurs when y equals 0. When y is equal to 0, what you're going to get is 0 is equal to 5x minus 2. And so you get that x is 2 over 5. And so the x-intercept is the point 2 over 5, comma 0. That's the x-intercept. For the y-intercept occurs when x is 0. So the y-intercept point is going to be when x is 0, y is negative 2. So 0 minus 2. And that's that. All right. I know my sketch is really off because a half would have been over here, but I'm just drawing something to see what was going on. All right. So the x-intercept, the y-intercept. Nice. Moving right along. It says let f of x be, let's go back. Let f of x be sine kx times sine aky. Determine dou 2f of xy of dou x by dou y. So we need to determine dou 2f of xy of dou x by dou y. To determine this right here now, that means we're going to differentiate with respect to y first, and then we're going to differentiate with respect to x. So let's go ahead and do that. We need to differentiate with respect to y first, and then differentiate with respect to x. Differentiating with respect to y first, we keep this first part as a constant. And so I'm not going to write all of this. I'm going to write fy. Fy really means dou f by dou y. So finding fy first, differentiating with respect to y. So this is a constant. So I'm going to get, oh, I don't need to do that. So the sine kx is a constant. So I just put back my sine kx multiplied by, now I can differentiate sine aky. When I differentiate sine aky, I get cos aky times the derivative of aky, and the derivative of aky, I could put it here, is a times k. All right, so that would be fy. Now next we need is dou 2f of dou x dou y. So we need to find now, differentiate it with respect to x now. So it's fyx. So fyx now. We need to differentiate fy now with respect to x. So we're going to differentiate this with respect to x now. Differentiating this with respect to x now, we're going to keep this part, a cos aky, as a constant. So differentiating this part with respect to x, I'm going to rewrite it as ak cos aky, just to show that that's a constant. Then when I differentiate sine kx, I get cos kx, then I multiply it by k. So the final answer is equal to ak squared. So the final answer is a times k squared cos aky times cos kx. Nice and easy. So that takes care of this question. Nice. All right. Now this question says use De Moivre's theorem to show that sine 5 theta is equal to sine to the 5th theta minus 10 sine cube theta times cos squared theta plus 5 cos to the 4th theta sine theta. To use De Moivre's theorem and do this, all we're going to show is, well, De Moivre theorem tells us that cos theta plus I sine theta so De Moivre's theorem tells us that cos theta plus I sine theta, let's write that down. De Moivre's theorem tells us that the cosine of theta plus I sine theta, when all of this is raised to the nth power, De Moivre's theorem tells us that it is equal to cos n theta plus I sine n theta. That's De Moivre's theorem. Cos n theta plus I sine n theta. So what does this mean? That means if we were to let n equal 5, if you let n equal 5, look what's going to happen. If you let n equal 5, you're going to get cos theta plus I sine theta to the n, which is now to the 5th power. You got cos theta plus I sine theta cos theta plus I sine theta raised to the n is to the 5th power, and this is equal to cos n theta, which is cosine 5 theta plus I sine 5 theta. Now all we need to do is expand this left hand side, and we would have learned Pascal triangle, its first term to the 5th. So this is going to work out to be cos to the 5 of theta. So you have to remember Pascal triangle, it is 1, 5, 10, 10, 5, 1. So it's cos to the 5th plus 5 cos to the 4, 5 cos to the 4 theta times I sine theta. Then you go 10 and it's going to be plus 10 cos cube plus 10 cos cube theta times I sine theta square plus 10 again, but now it is 10 cos square theta times I sine theta cube over following the pattern. It is 1, 5, 10, 10, then you go 5 again, and notice that we're decreasing in powers in cos and increasing in powers in I sine theta. So now it is plus 5 cos theta plus 5 cos theta times I sine theta to the 4 plus 5 cos theta plus I sine theta to the 5th. And that's how we expand all of that. Plus I sine theta to the 5th power. Nice. So finally we finish expand out all of this. Then what do we do next? What we do is now we're going to equate it to the right hand side, and the right hand side, which was just cos 5 theta cos 5 theta plus I sine 5 theta. Now when we equate it to the right hand side now, all you need to do is they want sine 5 theta. So that means that you're going to equate your imaginary parts. Equating your imaginary parts, you're going to go through and say, this is going to give me an imaginary number. Sine square is -1, so that's a real. This is going to give me an imaginary number. And this will give me an imaginary number. All right? So now that means that this now expanding the left-hand side with just the imaginary part. So we're equating imaginary parts now. All right. Equating imaginary part. Equating the imaginary part. What we're getting is 5 cos to the 4 I sine theta. Five cosine to the 4 I sine theta. I'm going to put the I on the outside here. So I times 5 cos to the 4 sine theta. For this part now, I'm getting I cube sine cube, but I cube is minus I, so I'm going to write it as minus I times 10 cos square times 10 cos square theta sine cube theta. And then right here I have sine I to the 5th. I to the 5th is just I. So then I just have I sine to the 5th and that's equal to I sine 5 theta. Nice. So to finish off this question now, we're almost complete. All right, so to finish off this question, all we have to do now is everything in the answer is in terms of sine to the 5th minus 10 sine cube plus 5 to the 4 cos theta sine theta. So we're done. All we need to do now is divide through by I, and dividing through by I, so we're going to put this part on the left part first. Dividing through by I, as you can see now, so when you divide through by I, you get sine 5 theta is equal to, when you divide through by I, this part becomes sine to the 5th theta, sine to the 5th theta, minus, well, plus, when you divide through by I, you get plus 5 cos to the 4th theta sine theta. Then you put now minus, divide through by I, you get minus 10 cos square sine cube. So minus 10 cos square sine cube theta. And that's your right hand side. That proves it. Soft. So we finish. That proves it. There it is. Minus 10 sine cube cos square. 10 sine cube cos square is the same as 10 cos square sine cube. 5 cos to the 4 sine theta. 5 cos to the 4 sine theta. Sine to the 5th. So we're showing it. Just put it in different order. So here it's shown. And soft with a capital T. Soft. Nice. All right. Now let's look at part D. Part D says write the complex number z in the exponential form. So in order to write this complex number z in exponential form, you first need to identify that z equal 1 minus I. That's in the second quadrant, because 1 is over here, minus, so this is 1. This is, let's say 1 is here, then minus, oh, it's in the fourth quadrant, my apologies. It's in the fourth quadrant. All right, it's in the fourth quadrant. So it's in the fourth quadrant. So we can find theta now. And so theta is just going to be equal to tan inverse of y over x. And so theta is equal to tan inverse of minus 1 over 1. That gives you, I think that's minus pi by 4. So that's the angle in the fourth quadrant. Then we need to find r. R is going to be equal to 1 square plus minus 1 square, all square rooted. And that's equal to the square root of 2. It's equal to the square root of 2. That is r. So now that we get this for r, we're good. So therefore we can write that z is equal to the square root of 2 e to the I times theta. So we're going to write it as square root of 2 times e to the theta, which is minus pi by 4, times I. That is z in this case. Nice. Moving right along, it now says, hence, show that 1 minus I to the 9 is 16 times 1 minus I. Okay. So, this is what we want. Hence, show that. Now remember, we just showed that z, which is equal to root 2 e to the minus pi by 4i. This is z, root 2 e to the minus pi by 4i, where we said that where z is 1 minus I. This is z is 1 minus I. All right, so all we need to do is go ahead and continue. So we need to just go ahead now and continue and raise this to the 9th power now. So z raised to the 9th power is going to be the root of 2 raised to the 9th power. Let me try to fix this. So z is just now the root of 2 raised to the 9th power. We're just raising it to the 9th power times e to the 9 times this now is e to the minus 9 pi by 4. Nice and easy. Now you may proceed, and how I like to do it, I like to then put it, I like to go from exponential to polar form. So in polar form, what this is saying is, in polar form, this is the root of 2 to the 9th power, and it is being multiplied by the cosine of minus 9 pi over 4, cosine of 9 pi over 4, plus I sine minus 9 over 4, minus 9 pi over 4. Nice and easy. So that's z to the 9 in this case, where z to the 9 is this. So z to the 9, which is this, is pretty much now saying that 1 minus I to the 9th power is equal to, put this in a calculator, root of 2 to the 9th power. So root 2 raised to the 9th power, root 2 raised to the 9th power is 16 root 2. So root 2 to the 9th power is 16 root 2. And 16 root 2 is multiplied by putting in a calculator the cosine of 9 pi by 4. So 9 minus 9 pi by 4. The cos of that is root 2 over 2. In this case, it's root 2 over 2. You can write root 2 over 2 as 1 over root 2. This is really 1 over root 2. Plus I sine minus 9 pi by 4. So minus 9 pi divided by 4. And the sine of that is minus 1 over root 2. So it's minus 1 over root 2 times I, when you put those in a calculator. And finally, all you have to do now is expanding the root 2, and so you're going to get 16 times root 2 multiplied by 1 over root 2 is 1 minus root 2 times minus 1 over root 2 is minus I. So we finished. So we proved it. Nice. That takes care of question 1. No issues. Moving right along. We get to question number 2. Question number 2 has integration. So it says that we're supposed to evaluate the integral of x to the 5th times cos x cubed. Now, typically I like to call these integrals I. I like to call these integrals I. All right? I like to call it I. If I'm going to use a substitution u, I'm going to use a substitution first, u as x cubed. Because I don't like to be integrating cos of like e to the x. You don't like to be integrating cos of these things. So anytime you say cos with a bracket, just call the thing in the bracket u. Cos. So u is x cubed. So that gives us that du is equal to, when we differentiate 3x squared, we differentiate x cubed, we get 3x squared. My apologies. So du is 3x squared. After we get du being 3x squared, we're good. So now I is going to be equal to, and remember du is 3x squared dx. So I is now going to be equal to, now this x to the 5th, let me put it down right here. X to the 5th can be broken up as x cubed times x squared. I can always separate x to the 5th as x cubed times x squared. So I'm going to rewrite this integral now as the integral of, instead of saying x to the 5th, I'm going to write it as x squared times the cos of x cubed times x cubed dx. And let me change the position. Let me put the x cubed here and the x squared here. And you might say, sir, so why you do that? Why did you break up x to the fifth? I broke up x to the fifth because I need to generate 3x squared dx to be du. So I need a 3 right here. So if I put a 3 right here, I'm going to have to put a 1 over 3 out here. All right. And now I can substitute for u. So now I get that I is equal to 1 over 3 times the integral of x cubed is u, so that becomes u. Cos x cubed now becomes the cos of u. And then 3x squared dx becomes du. So now we're good. When you get to this part now, we're going to use integration by parts now. This looks like by parts now. So now we can use integration by parts to do this. So to do integration by parts, we usually use u and v. Since I already use u and v, let me write down the by parts formula. Just for those who don't remember again, using by parts formula, the integral of u dv is equal to uv minus the integral of v du. That's the by parts formula. So if we're going to apply this by parts formula, what we're going to get now is this I is going to become equal to, we're going to think of this now, think of this as a u and this as a dv. So it's going to become, write the equal down here, it's going to be equal to 1 over 3 times 1 over 3 times uv. What's uv? This is like your u and your v. If cos u is your dv, when you might not be following. I'm going to use a different letter for u and v in this case. I'm going to use f and df. So in this case, I'm calling fu and so df equal 1. And in this case, I'm calling ds. I'm using f and s. ds, I'm calling ds cos u. And in this case, I'm calling s. When I integrate cos s, cos u, when I integrate cos, I get sine. When I differentiate sine, I get cos. When I integrate cos, I get back sine. So it's going to be u dv in this case, which is f ds, is equal to uv, which in this case is going to be fs, f times s. So it is u sine u. So it's 1 over 3 u sine u minus the integral of, this is now v du. In this case, it is now s df, which is now the integral of sine u. It's sine u du. And I close up that bracket. So now I can proceed. So finally, the answer I'm getting is 1 over 3 u. But remember, we said that u was x cubed. So it's 1 over 3 x cubed sine x cubed. Since I expand in the 1 over 3, it's going to become minus 1 over 3. Then the integral of sine u is minus cos, so it becomes plus 1 over 3 cos u. But remember, u is x cubed, so it's plus 1 over 3 cos x cubed. plus some constant of integration. I can call that k. That's how we do that question. Nice. Wasn't too bad. 1 over 3 x cubed sine x cubed plus 1 over 3 cos x cubed plus k. Nice. All right, 8 marks for that. Now the second part says find the integral of e to the 2x over the square root of 1 minus e to the 4x dx. So to do this integral, again, I like to call it I. I just like to call my integrals I. So I is equal to, I'm going to rewrite this as the integral of, instead of saying that, I'm going to write I is e to the 2x over the square root of 1 minus e to the 2x being square rooted. Instead of saying e to the 4x, I write it as 1 minus e to the 2x all squared. That is e to the 4x dx. I still can't see what's going on yet. So what I do is I do another u substitution. U substitution is so powerful. So I do another u substitution, and I'm going to substitute u as e to the 2x. If I substitute u as e to the 2x, then my du is going to be, when I differentiate e to the 2x, when I differentiate this, I get 2 times e to the 2x dx. So looking at the question above, I need to put a 2 right here, and so I put a half on the outside. Now that I do that, now I can rewrite that I is equal to a half the integral of 2e to the 2x dx is now du, so it becomes integral of 1 over the square root of, this part now becomes u, so it's 1 minus u squared, 1 minus u squared du. And so I is equal to, now when you're integrating 1 over the square root of 1 minus u squared, that's just sine inverse. So I is now just a half sine inverse of u. So it's a half sine inverse of u plus some constant c. That's how we attempt this question. But we can't stop right here. Never stop right here. Remember I said u is e to the 2x. And so you have to go further. And then finally you can conclude that, of course, in this case what we're saying is I is equal to a half sine inverse of u, where u is e to the 2x plus some constant plus c. That is I. Nice and easy, soft. That's how we do this. Nice. Now right here is, it says use partial fraction to show that x to the 4 plus 1 over x times x squared plus 1 all square is equal to 1 over x minus 2x over x squared plus 1 all square. Use partial fraction to show that. All right, let's go ahead and do this. I'm going to call this I because I don't want to write out back all of this. I'm calling all of this I. So I can be separated in partial fraction as a over x. I can be separated as a over x plus bx plus c over x squared plus 1 plus dx plus e dx plus e over x squared plus 1 all square. So this is I. All right. So now, of course, we're going to have to find the common LCM, primary school, mathematics, and prep school. So it's x times x squared plus 1 all square. And so we go x into this leaves x squared plus 1 all square. So it's going to work out to be a times x squared plus 1 all square plus this into this leaves x times x squared plus 1. So then it's going to be plus bx plus c times x. So it's bx plus c times x squared plus 1. And then we're going to go x squared plus 1 all square into this, just leaves x. Then it's going to be plus dx plus e times x. dx plus e times x. That's what we're going to get. All right, nice and easy, soft. So this is what we get now. Now, since this is what we get, all right, since this is what we get, now we can just proceed to go further and simplify this question. All right, so let's go. And we have to remember that this on the left-hand side, I is equal to this. So since I is equal to this, before we even simplify, remember I is all of this, we can just equate the numerators. So equating the numerators, that means that, let me put in, that's what we did right here, equating numerators. Equating the numerators, we are going to see that x to the 4 plus 1 is equal to all of this. So let me go ahead and work out what all of this is. X squared plus 1 all square is x to the 4 plus. So expanding this, I would get ax to the 4 plus 2ax squared plus a. That's what I get when I expand that side. Then when I expand right here now, I'm going to get bx squared plus cx. This is really bx squared plus cx, and then bx squared times x squared is bx to the 4, and then bx squared times 1 is just plus bx squared, and then I'm going to have cx times x squared is cx cubed, and then I have cx times 1 is just cx, and then I have dx times x is plus dx squared, and then I have e times x is just plus ex. Nice. It looks confusing, but it's very easy. What you're going to do now is you equate coefficients of each of them. So equating coefficient of x to the 4, we see that we have x to the 4 here, ax to the 4, bx to the 4. And so equating coefficients, equating x to the 4 terms. So this means equating x to the 4 terms. We can see that we're getting 1. The coefficient of x to the 4 is 1, is equal to a plus b. So 1 is equal to a plus b. Equating x cubed terms, there's no x cubed term here. So equating the x cubed terms, realize that 0 is equal to x cubed term over here is c. Cx cubed, so 0 is equal to c. And then equating x squared terms, there's no x squared term over there, and so 0 is equal to x squared term over here is 2a plus b. So 0 is equal to 2a plus b plus d. Then finally equating x terms, or penultimately equating x terms, we have cx plus ex, and there's no x term is 0, so 0 is equal to c plus e. And then finally equating our constants. The only constant we're getting is a, and so a must equal 1. This is equating constants. Now if a is equal to 1, and from equation 1 here, a plus b is 1, so that implies that b must be 0. b is equal to 0. And b is equal to 0. b is equal to 0. And we can see right here c is equal to 0. And since b is equal to 0 and c is equal to 0 right here, it implies that a is 1, and so 2 plus b, 2 plus b, so 2 plus d is 0, so d must be negative 2. d must be negative 2. And if c is 0, 0 plus 0 is 0, so e must be 0. e must be 0. So these are all the solutions. All right, nice. And so looking at it now, finally we can conclude now that that expression which we can call I is equal to a over x. A is 1, so it is 1 over x, plus bx plus c over x squared plus 1. But bx plus c is 0, so we can just forget that part, as we're really getting plus 0x plus 0 over x squared plus 1. But 0x plus 0 is just 0. All of this is just 0. All of this is 0. And then we have plus dx plus e. dx plus e, dx, that's just minus, because d, it have a minus, so it's minus 2x plus e, but e is 0 over x squared plus 1 all squared. So we're showing it. And remember that this is equal to this. So we're showing it, and we're nice. So we're nice, man, we're nice. We're showing. Soft. Nice. Then it says, hence integrate this. Hence, integrating this means we're going to use what we just found out. So again, I'm going to call it I. Since I'm calling it I have now that I is equal to, instead of integrating this, we're integrating instead 1 over x minus 2x over x squared plus 1 all square dx. This is what we're integrating. Now, we can always break them up into two separate integrals to say we're integrating 1 over x minus, I know I left off my dx, I know, minus the integral of 2x over x plus 1 all square. Don't leave off your dx. I leaving off the dx, but you don't. So I just separate it now into the sum of two integrals, or the difference of two integrals. All right, and so now the integral of 1 over x, you get ln x. You can put mod x if you want, it don't matter. So ln x, some people like to put ln mod x, just depending. All right, ln x minus the integral of this now, minus the integral of this. Now I'm going to use u substitution here. So I'm going to let u be equal to x squared plus 1 or x squared plus 1. If I use a u substitution here, I realize that du would be 2x. And so I can use u substitution and integrate this. And so this becomes minus the integral of, in the numerator is du, and here is just u squared. So it's minus the integral of 1 over u squared du. And so what I'm getting is ln x, and it's ln mod x. Now to integrate u squared, it's going to become add 1 to the power, which is u to the minus 1, divided by the power of minus 1 plus c. Now what was u? Substitute back what was u. So this worked out to be ln the modulus of x, ln the modulus of x, minus and minus give you plus, so ln mod x plus, u to the minus 1 is really 1 over u, so that's going to be plus 1 over u, u is x squared plus 1, plus c. Nice and easy, soft. So that's how we do this question. Nice. That's part 2. Now we're moving right along. We get to section 2, which is module 2. And we're going to do this question. It says, a sequence is defined such that a1 is equal to the root of 2. And it says that an plus 1 is equal to root 2 plus an. And so to go ahead now and find the third term a3. So to find the third term a3, the third term is equal to the square root of 2 plus an when n is 2. This is now a2. And so a3 is equal to, what's a2? In order to find a3, I need to find a2. So first we need to find out what a2 is, where a2 is equal to the square root of 2 plus a1. And so I'm getting that a2 is going to be the square root of 2 plus root 2. That's a2. 2 plus root 2 square rooted. And so a3 is actually the square root of 2 plus the square root of 2 plus the square root of 2. That's a3. A lot of work. So I'm going to put it in decimal. 2 plus root 2 square rooted is 1.84. So a2 is 1.84. And so 1.84 plus 2 square rooted is 1.96. So a3 is 1.96. a2 is 1.84. We had to find a2 before we could find a3. Nice. Now the next part says, use mathematical induction to prove that xn is increasing and that it is bounded above by 3. So to show that xn is increasing and that it is bounded above by 3, it wants us to show that an is less than an plus 1 and an is less than or equal to 3. So all right, let's go ahead and work this out. All right, let's go ahead and work this out. It says prove it by induction. So we start from when n is equal to 1. When n is equal to 1, let's do it pretty. All right, when n is equal to 1, when n is equal to 1, we have that a1 is equal to root 2 and a1 is equal to root 2, which is equal to 1.41. That's root 2, which is less than a2, because remember we showed that a2 was 1.8 something, 1.84. So a1 is less than a2. Also a1 is less than or equal to 3, clearly, because if it is root 2, it's less than or equal to 3, and so n equal 1 is true. So n equal 1 is true. All right, n equal 1 is true. Now for n equal k, what we're going to have is ak is less than ak plus 1. So ak is less than ak plus 1, and ak plus ak is less than or equal to 3. And we're going to assume this is true. Assume true. All right, so next now, we're going to go for n equal to k plus 1. So now for n equal k plus 1. Where n is equal to k plus 1. For n is equal to k plus 1, what we are going to have now is, for n is equal to k plus 1, for n is equal to k plus 1, now we're going to have ak plus 1 AK plus 1. But remember, AK plus 1 is equal to the square root. AK plus 1 is equal to the square root of 2 plus AK, don't it? Yeah, man. AK plus 1, this is what AK plus 1 is equal to. But look at this now, this pretty magic that we're gonna do now. Pretty magic. We're gonna make it look nicer than this. Let's do it in a pretty way. So we're gonna start by saying AK is less than. We're gonna start by saying AK is less than 3. AK is less than 3. Then we're gonna add 2 to it, and so 2 plus AK, 2 plus AK is less than 5, less than or equal to. Then we're gonna square root both sides and say now that means that the square root of 2 plus AK, the square root of 2 plus AK is less than or equal to the square root of 5, and the square root of 5 is less than or equal to 3. Yeah, man, the square root of 5 is less than 3. But then the root of 2 plus AK is AK plus 1. And so we showed now that AK plus 1 is less than or equal to 3. So get the first proof out of the way. So prove this one. No need to prove that AK plus 1 is less than AK plus 2. Now what is AK plus 2? AK plus 2 is going to be 2 plus the square root of AK plus 1. So let's prove that. So let's draw over here in black line. So start by saying AK plus 1. Remember AK plus 1, this is what we have first. For n equal K plus 1, we know how, so we prove this one. Now we need to show that AK plus 1 is less than AK plus 2. Now AK plus 1 is going to be equal to AK plus 1. We know this is the square root of A plus AK plus 2. I want to fix this up. Is there some more space? Let me check around here because we don't like to squinch. All right, we get some more space. So now the second part we need to show, remember, we need to now show that AK plus 2 is bigger than AK plus 1. That's what we need to show now. This is what we need to show. So now in order to show that, we'll start by saying, well, AK plus 2 is equal to, AK plus 2 is equal to what? AK plus 2 is equal to 2 plus AK plus 1 square rooted. That's AK plus 2. I'm just writing that down. All right, this is AK plus 2. All right, this is AK plus 2. But what is this? This is now the same as, remember, AK plus 1 is the square root of 2 plus AK plus 1 now is AK plus 2 square rooted. So this is AK, all right? This is now AK plus 2. But this right here that we have must be greater than, this is definitely greater than just AK plus 2 square rooted. And this AK plus 2 square rooted is just AK plus 1. And so this implies that AK plus 1 is less than AK plus 2. All right. Now, many persons may not necessarily appreciate this proof. It depends on how your teacher may have taught you this. Or it's just depending on how you would have learned it at the Unit 1 level. All right. So many persons may want to use, many persons may not appreciate this. So let me put an alternate. This is a OR. This is a OR proof. An OR proof is to start by writing down what we know. We know that AK is less than AK plus 1. This is something that we know. AK is less than AK plus 1. But what is AK? We know that AK is, of course, 2 plus the square root, 2 plus AK square rooted. This is why starting with what we know. All right, we know that this is AK. So let's say we want to now generate, a AK plus 2. So to generate a AK plus 2, all right, we first need to add 2 to both sides. Add 2 to both sides. So you want to add 2 to both sides now, so you get 2 plus AK. So I'm just doing the alternate proof. 2 plus AK is going to be less than 2 plus AK plus 1. And then you can square root both sides. Take the square root now of both sides. So the square root of 2 plus AK is less than the square root of 2 plus AK plus 1. But the square root of 2 plus AK, that's just AK plus 1. And so AK plus 1 is definitely going to be less than AK plus 2. So depending on how you would have done it in Unit 1, and a lot of teachers like to use the fact that this, you need to use AK to show the AK plus 1 statement. So depending on how you learned it, you could have used either proof, and that is true. And so therefore N equal K plus 1 is true. So therefore N equal K plus 1 is true. And so hence by PMI, the statement or the sequence statement given is true. The statement given is true for all natural numbers. Nice and easy, soft. So that's how we do this question. Here and here, completed. Part B. Part B says, let f of x be equal e to the minus x squared by calculating the first 3 non-zero terms by assuming that the pattern continues. So show that the Maclaurin series expansion of f of x may be expressed as f of x is equal to the sum from k equals 0 to infinity of minus 1 to the k of x to the 2k over k factorial. So we need to just find the first three non-zero terms. Let's go ahead and do that. Find the first three non-zero terms by calculating the first three non-zero terms. Okay, using Maclaurin series, this is Maclaurin series expansion. I just like to write down the formula. F of x using Maclaurin series, we know that f of x is equal to f of x is equal to f of 0 plus f prime of 0 times x plus f double prime of 0 times x squared over 2 plus f triple prime of 0 times x cubed over 3 factorial, and 3 factorial is 6, 0 over x cubed over 3 factorial, and it continues. So this is Maclaurin formula. So first let's find out what is f of 0. So f of 0 will be equal to, plugging in when x is 0, we get e to the minus 0. E to the minus 0 is 1, so f of 0 is 1. Now we need to find what is f prime of x. Now f prime of x is going to be equal to, we differentiate minus x squared to get minus 2x e to the minus x squared. And so that means that f prime of 0, that means that f prime of 0, when I plug in 0 here, I'm going to get 0. That means f prime of 0 is 0. Since f prime of 0 is 0, I am good. That means this is a 0 term, so I still need to find another term and another term. I only have one non-zero term so far. So now I need to find f double prime of x. To find f double prime of x, I'm going to have to use product rule and differentiate this as a product. So I keep the first, which is minus 2x, times the differential of the second. Differential of the second is just minus 2x e to the minus x squared plus, I then keep the second, which is e to the minus x squared, times the differential of the first, and the differential of the first is minus 2. All right, so keep the first, differentiate the second, plus keep the second, differentiate the first, and so then I get f double prime of 0 is equal to, I can plug in 0 over here, I'm going to get 0, but over here when I plug in 0, I will get, that looks like, plugging in 0 here, I will get, this is 1 minus 2. I will get minus 2. So I only have two non-zero terms so far, so I need to differentiate again. Now, this is really, this together is really, minus 2 times minus 2 is really 4, and x times x is x squared. So I want you to look at this now as 4x squared. Look at this as 4x squared e to the minus x squared, because we're going to have to use product rule again. Using the product rule again, you get the third derivative, f triple prime of 0 and f triple prime of 0 using product rule is equal to keep the first, 4x squared, keep the first, times the differential of the second. We differentiate e to the minus x squared. We get keep the first, differentiate the second. We get minus 2x e to the minus x squared plus keep the second plus keep the second, which is now your e to the minus x squared, times the derivative of your first. When you differentiate 4x squared, you're going to get 8x. And then you're going to have to differentiate e to the minus x squared times minus 2. When you differentiate this, you get differentiate minus 2e to the minus x squared. Differentiating just the e to the minus x squared, you get minus 2x. And minus become plus. So you're going to get 4x e to the minus x squared. Nice. So now you can go ahead and find f triple prime of 0. So f triple prime of 0 is equal to, plug in x as 0, you get 0. Plug in x as, oh my golly, this won't be good. This is giving us 0. That's giving us 0 plus this is also giving us 0. This is also giving us 0. Oh my golly, so we're gonna have to differentiate one more time. And you might ask why? Because we need the first three non-zero terms. So far, we only have one non-zero term here, another non-zero term here, and so we need one more non-zero term. Oh boy. So we're gonna have to differentiate yet again. So let's go differentiate again. So let me make space and do the derivative here. Once I have space to do all the derivatives right here. So I was getting f triple prime of 0 is equal to 0. And so now we can get to the fourth power now. The fourth derivative of x, we're going to have to use product rule again. This part, look at this now as minus 8x cubed. So you keep the first, look at this as minus 8x cubed. So you keep the first, which is minus 8x cubed. Keep the first, differentiate the second, which is e to the minus x squared. When you differentiate that, you get minus 2x. You get minus 2x e to the minus x squared plus you keep the second, which is keeping the second is e to the minus x squared times the derivative of the first is plus the derivative of the first is going to be minus, carry down the power. That's what? Carry down the power. 8 times 3 is minus 24x squared. You get minus 24x squared e to the minus x squared plus Now we need to differentiate this here. Differentiating this, we use product rule again. Look at this as 8x e to the minus x. So we keep the first 8x times the derivative of the second. We differentiate the second, we're going to get minus 2x e to the minus x squared plus, keep the second. The second is e to the minus x squared times the derivative of the first, which is 8 plus 8 e to the minus x squared. So now we differentiate this one complete. Now we need to differentiate this one with respect to x again, plus keep the first, which is 4x, times the derivative of the second. So it's going to be 4x times derivative of the second is minus 2x e to the minus x squared, plus keep the second, which is e to the x squared times the derivative of the first, which is 4. So you get 4 e to the minus x squared. Plugging in 0, you're going to get 0, 0, 0, 0. Plugging in 0 here, you're going to get 0. This is 1, 12. So you're going to get f to the 4 is 12. You're going to get f to the 4 of 0. That is equal to 12. So now we can finally say then that f of x is now going to be equal to f of x is equal to f of 0. F of 0 is 1 plus f prime of 0. That one was 0 times x plus f double prime of 0. F double prime was minus 2. So it's minus 2 times x squared over 2 factorial plus f triple prime, that was also 0, plus f to the 4, which is 12, x to the 4 over 4 factorial. 4 factorial is 24. So in other words, what we're getting is f of x is 1. This minus 2 cancels the minus 2. This minus 2 cancels 2. So you get 1 minus x squared plus 1 minus x squared plus a half x to the 4. Nice, so this is what we get. And I think they said show something. Show that it can be expressed as f of x being the sum from k to infinity of minus 1 to the k of, no. To show that it can be that, I'm just going to put a line right here. And I'm going to evaluate that sum. And it should look something like this. So the sum from k equal 0 to infinity of sum from k equals 0 to infinity of minus 1 to the k times x to the 2k. This is minus 1 to the k times x to the 2k over k factorial. Let's see. When you put k as 0, you're going to get 0, or minus 1 to the 0 is 1, x to the 0 is 1 over 1, so you get 1. Put k as 1, you get minus 1. K as 1, now you get x squared over 1 factorial, so you get x squared. Put k as 2, you get minus 1 squared, which is 1, so it becomes plus. X squared is 2 times 2 is 4, so you get plus x to the 4 over k factorial. X is 2, 2 factorial is 2, plus, and it continues. And so they're the same. So we can say hence, the statement is sure. Hence f of x can be expressed as that summation. So we did it. Nice. As you can see, we're getting the same thing when we expand it. Nice. Hence or otherwise determine the values of x for which the expansion is valid. So we need to determine the values of x for which this expansion is valid. Okay, let's see how we're going to determine the values of x where this expansion is valid. All right. If we were to plug in, let me look back at the original function. This is an exponential function, and so this should be valued exponential function. This should be valid for, and it said hence or otherwise. Okay, otherwise. So we can go otherwise as well. So this expression, this is f of x. Anyway, this is f of x, e to the minus x squared. Let's see if we were to plug in a negative value for x. Once you square it, it becomes positive. And once you square it, it becomes positive. E to a positive number, whatever x is, let's say x is 5, e to the minus 5 square. E to the minus 5 square, that's going to be 5. E to the minus 5. E is always positive, so it's valid for all x. All right, so this expansion has to be valid for all x. So that's how I would do it. So let's write that down now. So we can say, it says hence or otherwise. I'm going otherwise. So I am going f of x is equal to e to the minus x squared. E to the minus x squared. Now, as we can see right here, e to the minus x squared, this will always be valid, meaning this function. So first we can go for any x, let's write it down properly. For, why is it not writing so well right now? So this symbol means for all x, minus x is an element of real, which implies that minus x squared will also be giving you some real number, and so e to the minus x squared will most likely be valid as well. E to the minus x squared, this will always give you some positive number. This will also be always greater than 0. This will always be greater than 0 no matter what x is. This will always be greater than 0, which implies that the function, which implies the approximation for f, so which implies the approximation for x is valid for all x. All right, that clearly makes it valid. So any x value you plug in, it's gonna be positive. So 50 e to the minus 50 squared so you put in e to the minus 5, you put in e raised to the minus 5 squared. Anything you get in, it might be a very small number, but its approximation will always be valid. All right, so it's going to be valid for all x. Part C. Deduce the sum of this series. So to deduce the sum, this looks like method of differences. So first we're going to plug in when n equal 1. We're going to get the sum of, this is now plugging in n as 1. We're getting the sine of 1 plus the sine of, plugging in n as 1, n as 2, now you get 1 over 2 plus the sine of, plugging in n as 3, you get the sine of 1 over 3 plus plugging in all the way down, plugging in the last term, n as infinity, which we can't necessarily do. 1 over infinity is 0. So 1 over infinity is 0. And so when you plug in infinity, you're getting the sine of 1 over infinity is 0, which is sine 0, minus, starting from here, plugging in n as 1, you're going to get the sine of a half plus the sine of 1 over 3 plus, you're going to keep on doing this until you plug in infinity again, and you're just going to get plus sine of 0. Then you can do the subtraction. Doing the subtraction, what we notice is sine a half will cancel a sine a half. Sine 1/3 cancels sine 1/3. This don't cancel this. Sine 0, sine 0. So what we're left with is just sine 1 minus nothing. So we're just left with this being sine 1. So the answer is just sine 1. Whoa, that's crazy. The answer is sine 1. Sine 1. That's the answer. This works out to be sine 1. Just want to check this again because 4 marks, it should have been 2. Let's check it again. Plugging in 1, sine 1. Plugging in n as 2, sine a half. Plugging in close to the last term would be sine 1 over n minus 1. Then n infinity now, sine 0, yep. Plugging in 1 here, we get minus 1, we get sine a half. Plugging in 2, sine 1 over 3. Yep, sine 1 is the answer. Easy 4 marks. So finish that one now. Moving right along, question 4. Determine the coefficient of the x to the 7th term in this expansion. So we want to find the coefficient of x to the 7 in this expansion. To find the coefficient of x to the 7, fairly simple. So let's go ahead and do that. To find the coefficient of x to the 7. To determine the coefficient of x to the 7, we're going to have, I'm going to call it the term x to the 7, x to the 7th term. To find that, we first need to find the sum Let's see which term will give us this. So we just need to write down that we need the x to the 7th term, which is we need to choose r from n, where n is 8, of x squared to the n minus r times 3 over x to the r. I'll need this to give us the answer times x to the 7th. So what we're going to do is multiply this across to find out what r is. Once we get what r is, we can plug it back into this formula. So we have x squared to the n minus r. N is 8, by the way. So it's going to be x to the 2 times 8 is 16. X to the 16. X to the 16 minus 2r times 3 to the r over x to the r. And this is equal to ax to the 7. We want it to be equal to x to the 7. So let me see now. When the bases are the same and we're dividing, we can subtract the powers. So really and truly what we're saying then is x to the 16 minus 3r is equal to x to the 7. And so we can use that to find what is r. So 3r is equal to 16 plus 7. Let's check again to make sure this is fine. 8 choose r, x squared to the 8 minus r. Oh, this is minus 3 over x, by the way. Minus 3 over x. Minus 3 over x. So it's really being multiplied by x to the minus r. This is really x to the minus r up here. So it's minus r plus 16 minus 2r. That's minus 3r. I'll need it to be something times x squared. So we're getting that 3r. 16 minus 3r is 7. That's not working out. 3r is 16 minus, bring over here, bring over here. R equal 9, R equal 3. R equal 3. It's R3. So let's check it now. If R is 3, we're good to go. So I'm getting R is 3. Since R is 3 now we can find the coefficient. Now we can just use this formula, putting in R as 3. So it's going to be 8, choose 3. 8 choose 3 of x squared to the 8 minus 3, because r is now 3, 8 minus 3 is 5, times minus 3 over x cube. This will give us the coefficient. So 8 choose 3, I'm getting 8 choose 3 is 56. So this is 56 x to the 10th power times minus 3 cube, which is minus 27, over x cubed So what I'm getting is this is equal to 56 times minus 27 minus 1,512 minus 1,512 x to the 7th. And so the coefficient is minus 1,512. Let's write that down. So the coefficient of x to the 7th power is minus 1,512. That's what we get. Nice. Moving along. It says, by expressing n choose r and n choose r minus 1 into factorials, show that n choose r plus n choose r minus 1 is n plus 1 choose r. So let's do this. To express n choose r in factorial, n choose r in factorial is n factorial over r factorial times n minus r factorial plus n factorial over r minus 1 factorial times n minus r minus 1 factorial. And n minus r minus 1 is going to be n minus r plus 1 factorial. So now I need to add these. All right, so the common LCM is going to be r factorial, and I'm going to have n minus r plus 1 factorial this into this leaves n minus r factorial. So in the numerator, I'm going to have n factorial times n minus r factorial plus this into this into this leaves n factorial times n minus r plus 1 factorial. I forgot the plus 1. Plus 1. Primary school maths is just with letters. And then this into this. R minus 1 factorial into this. R factorial divided by r minus 1 factorial. You have to remember that this just becomes r factorial is really r times r minus 1 factorial. That is r factorial, r times r minus 1 factorial. So this into this leaves r, and so it's going to be this into this leaves r, so it's going to be r times n factorial. Remember, we're adding them plus this. So all we need to do is factor out n factorial from the numerator. Factor out n factorial from the numerator, and you get n minus r plus 1, n minus r plus 1 plus r over r factorial times n minus r plus 1 factorial. All right. Just want to check to make sure I didn't make any mistake. Let's check it over again. Listen to this, n minus r into n. Oh, here's the mistake. A mistake was made here. N minus r. Think of n minus r as 5. 5. And so n minus r plus 1 is like 6. 6 factorial. 5 factorial into 6 factorial would leave 6. Right? So what am I trying to say? Want to make it bold and vivid. Think of this as k. Think of, let k be equal to n minus r factorial. Think of that as k. Let's make it clear. And so k plus 1 factorial, k plus 1 factorial would be equal to n minus r plus 1 factorial. That would be k plus 1 factorial. And then if you were to find out what is k plus 1 factorial over k, it would just be k plus 1. K factorial over k. K plus 1 factorial over k just leaves k plus 1. So we're supposed to just get k plus 1, which is n minus r plus 1. So it's n minus r plus 1 without the factorial. That's the mistake. Remove this factorial sign. So then we factor n factorial, good. And so now we're getting, finally, n minus r plus 1 plus r. The minus r and the plus r cancel, so we're left back with, in the numerator, n factorial times minus r plus r cancel, so it's n factorial times n plus 1 over, this is now r factorial times n minus r plus 1, r factorial times n minus r plus 1 factorial, and that's equal to, now n factorial times n plus 1 is n plus 1 factorial. So I'm going to rewrite this as n plus 1 factorial over, instead of having it as n minus r plus 1, I'm going to rewrite it as r factorial times, I'm going to rewrite it as n r factorial times n plus 1 minus r factorial. Now think of n plus 1 like x. Think of n plus 1 as like a x. Then if we think of n plus 1 like some x, then really and truly, this is just if n plus 1 is a x, we have x choose r. But then what is x? N plus 1. So this is just n plus 1 choose r. So finally we prove it, that thing up there is equal to n plus 1 choose r. Nice and easy, soft. So prove it. Be nice. All right, nice and easy, soft. Continuing right along, it says, use the intermediate value theorem to show that this equation has a root on the interval 1 and 1.5. So all you need to do to show this is first find out what is f of 0. F of 0 is going to be equal to 4 cos 0, 4 times the cos of 0. Oh, it says 1. 4 times the cos of 1 minus 1 cube, which is 1, plus 2. What you get is 4 cos 1 minus 1 plus 2, 4 cos 1 minus 1 plus 2. I get 3.16, which is greater than 0. And this is for f of 1. Then I need f of 1.5. Now f of 1.5 is going to be equal to 4 cos 1.5 minus 1.5 cubed. 1.5 cubed is 3.375 plus 2, and that's equal to 4 cos 1.5 minus 3.375 plus 2, that's negative 1.09, and that is less than 0. Nice. Since this is less than 0, we realize that f of 1 is greater than 0 and f of 1.5 is less than 0. So if you were to make a sketch, you have some curve. Let's say here is 1 and here is 1.5. F of 1 is 3 point something. F of 1.5 is negative something. So the curve looks something like this. All right, this is 3.1, 3.1, and this is negative 1.1. And so clearly by IVT, so by IMVT, don't you need to start with that? Let's start by saying since f of x is continuous on the interval, since it's continuous on the interval 1 to 1.5, and f of 1 is greater than 0 and f of 1.5 is less than 0, then hence f of x, since f of x is continuous on the interval, f of 1 is greater than 0 and f of 1.5 is less than 0, hence f of x has a root on the interval. It has a root on the interval 1 to 1.5. Nice and easy. So that's that question. Nice. Now this question now says, use linear interpolation to approximate the value of the root of the equation 4 cos x plus 4 cos x minus x cubed plus 0 on the interval 1 to 1.5, correct the 2 decimal place. Now approximation of the root using linear interpolation is x is equal to a times the modulus of f of b plus b times the modulus of f of a over the modulus of f of a plus the modulus of f of b. This is the formula for linear interpolation. That's the formula that we use for linear interpolation, the modulus of f of a plus the modulus of f of b. Nice. So since we're going to be using this formula, your a, what is your a? Your a is your starting point on the interval, which is 1, and it's multiplied by your f of b, which is f of 1.5. We found f of 1.5 to be minus 1.09, but the modulus of it makes it positive. So it's 1.09 plus, what is your b? Your b is your closing value in the interval 1.5 times f of a. F of a is f of 1, and we found f of 1 to be 3.16. So that's 3.16 over f of a plus f of b, and it's the modulus of them. So it's over 1.09 plus 3.16. So you add these two together to get what is x. That will give you your answer. So 1.09 plus 1.5 times 3.16 divided by 1.09 plus 3.16. I'm getting 1.37. Getting x as 1.37. That's correct to 2 decimal place. Remember, the question said 2 decimal place. Getting 1.37. That's an approximation of the root. Nice. But it gives 8 marks. So what it wants us to do? Should we continue? Use linear interpolation to approximate the value of the root in the interval. I guess we should continue. He didn't say use it to approximate the roots. Why is it 8 marks? So since it's 8 marks, we're going to continue. We're just going to repeat. All right. So if you were to put in f of 1.35, 1.37, f of 1.37 would be 4 times the cosine of 1.37 minus 1.37 cubed plus 2. That's 0.22. That's 0.22, which is greater than 0. So that means that we've reduced it down. We've reduced down the interval that the root lies on. The interval the root then lies on. Which one was negative again? The 1.5 was negative. So the root then lies on 1.37 and 1.5. So we're going to use linear interpolation again, because it says 8 marks. I don't know how many times, but I guess until we get 0.00 something, we'll stop. So continuing, we're going to get x is equal to a in this case is 1.37 times f of b. F of b is going to be f of 1.5, which we found was 1.09, plus 1.5 times f of a, which is f of 1.37. F of 1.37 found is 0.22. 0.22 divided by 0.22 plus 1.09. 0.22 plus 1.09. So going again, we're getting that. This is the second approximation, x2. So the second approximation is 1.37 times 1.09 plus 1.5 times 0.22 divided by 0.22 plus 1.09. We get 1.39. Getting 1.39. Now what we need to do is find out what is f of 1.39. Let's find that out. F of 1.39 is going to be equal to 4 cos 1.39 minus 1.39 cube plus 2. I get in 0.03. Getting 0.03. So if we go one more time, this really close. If we're to go one more time, that means the root lies on the interval. The root lies on 1.39, 1.5. So using linear interpolation one more time, we're going to get that x3 is equal to a, which is now 1.39, times f of b, which is 1.09, plus b, which is 1.5, times f of 1.39, which is 0.03, over f of b plus f of a, which is 0.03 plus 1.09. So what we're getting for the third approximation of the root is, put that in a calculator, 1.39 times 1.09 plus 1.5 times 0.03 divided by 1.12, you get 1.39. So I'm getting 1.39 again. Since I get 1.39 repeated, it is fair to say that hence 1.39 is an approximation of the root, because it's repeated. So 1.39 must be the approximation of the root. So you can stop here. How did I predetermine where to stop? I'm getting the root repeated, so you can stop right there. Finally, this part says the equation 3e to the x minus 3e to the x is equal to 1 minus 2 ln x is known to have a root on the interval 0, 1. Taking the first approximation of the root to be 0.2, use the Newton-Raphson method to find the second approximation of the root. So to do this, well, what we do is we have 3e to the x is 1 minus 2 ln x. So make this equation equal 0 by bringing it over to the other side. So I'm going to rewrite the equation as 3e to the x, 3e to the x plus 2 ln x. It's not coming out good right now. Let's retry that again. Let's rewrite it. So we're going to call the function g of x. G of x is equal to 3e to the x minus 2 ln x when you bring it over, it becomes plus minus 1 equals 0. So now that this is g of x, we need g prime of x now. So g prime of x is going to be, to differentiate 3e to the x, you get 3e to the x plus, you differentiate 2 ln x, you get 2 over x. So now what are you required to do? You're required to find g of 0.2. So put x as 0.2 in this equation to get 3 times e raised to the 0.2 plus 2 ln 0.2, and you're going to get 0.445. So it's g of 0.2 is 0.445. Nice and easy. The next thing now is we need g prime of x. So we need g prime of 0.2, g prime of 0.2. To find g prime of 0.2, well, we just plug in x as 0.2. So we're going to get 3 times e raised to the 0.2 plus 2 divided by 0.2. I'm getting 13.66. And to use the Newton-Raphson method, the second approximation x2 is equal to x1 minus g of x1 over g prime of x1. Moving right along and working this out. And so working this out, what we're going to get is x1. What is x1? x1 is 0.2. So we'll get 0.2 minus g of x1. What is g of x1? G of x1 is, what did you get for g of x1? Oh, 0.445 over g prime, which is 13.66. And so we take the difference now, and that will give us x2, which is 0.445 divided by 13.66. 0.2 minus that, we get 0.167. 0.167. So that's the approximation of this root. Nice and easy, solved. So 0.167. So 0.167 is the approximation of the root, or is the second approximation. Nice and easy. Nice. All right. We finally get into module 3, the best module. And it says events A and B are such that the probability of A is 0.4, the probability of B is 0.45, the probability of A union B is 0.68. Find the probability of A intersect B. The probability of A intersect B, that is equal to the probability of A plus the probability of B minus the probability of A union B. And so what we're going to get is the probability of A intersect B is equal to the probability of A, which is 0.4, plus the probability of B, 0.45, minus the probability of A union B, which is 0.68. We work that out, 0.4 plus 0.45 minus 0.68, and so we get 0.17 is the probability of A intersect B. Now determine whether A and B are independent. Now let's check it. The probability of A times the probability of B, that's going to be equal to the probability of A is 0.4 times the probability of B is 0.45. When you multiply those two together, you get 0.4 times 0.45. You get 0.18. Now the probability of A intersect B is equal to 0.17. Now since they are not the same, since the probability of A intersect B is not equal to, let me write it out. They are not independent pretty much. So since we realize that the probability, yes, I want red, the probability of A intersect B since the probability of A intersect B is not equal to the probability of A times the probability of B, then A and B are not independent. So A and B are not independent events. That's that. Moving right along. This question says, a committee of 4 persons is to be chosen from 8 people, including Mr. Smith and his wife. Mr. Smith will not join the committee without his wife. He's a good husband, but his wife will join the committee without him. Okay, so he's only gonna go if his wife is there, which probably means that it's a committee that he doesn't really want to be on, but his wife is telling him, all right, we need to do this, but you know, if she's not gonna be there, he's not gonna be there. It's probably more of an interest to her than to him. Let's assume that. That's the only reason why she will join without him, but he won't join without her. So calculate the number of ways a committee can be formed. So the committee can be formed. So possible, let's look at case 1. Case 1 would be Mr. Smith and Mrs. Smith on the committee. Let's look at that case first. I know I spell committee wrong, so be it. So if both of them are on the committee, we're choosing those 2 already from 2 times. We can only then choose 2 other persons from the 6. So that will give us 2 choose 2 times 6 choose 2, which is 15. So there are 15 ways in which both of them can be on the committee. Let's look at case 2. Case 2. Case 2 is Mrs. Smith on the case 2 is pretty much Mr. Smith on the not on the committee. Mr. Smith not on the committee. So if Mr. Smith is not on the committee, but his wife is still on the committee, then Mr. Smith is not on the committee. So he's definitely out. So you're really just choosing the other people. So he's out. So you're just choosing 7 You're choosing 4 from 7. So you're choosing 4 from 7. So 7 choose 4 is equal to 35. And so that's it. And so the total possibilities is equal to 15 plus 35, which equals 50. That's the total number of ways this committee can be formed. Nice and easy, soft. All right, this question says, how many 8 digits greater than 500,000 can be formed with digits 2, 3, 4, 5, 6, and 7 without repetition? Without repetition means we're not repeating any digit. And if we're not repeating any digit, then let's go ahead and look at not repeating any digit. So not repeating any digit would mean we have not repeating any digit, as I said. So that means we're looking at case 1. It must be an odd number. So that means the number ends with 3. Let's look at case 1 where the number ends with 3. So you have 6 digits, 1, 2, 3, 4, 5, 6. So if the number ends with 3, so this has to be number 3 go here. So there's only one way. Now the number must be greater than 500,000. So you can either select 5, 6, or 7 right here. So you have 3 numbers can go here. So now after you take out these 2 numbers, you're left back with 4 numbers. So 4 number can go here, 3 number can go here, 2 number can go here, then the 1 number go there. So case 3 has how many ways? That's going to be 3 times 4 times 3 times 2 times 1, which is 3 times 4 times 3 times 2 times 1. That's 72. There are 72 ways where it can end with 3. Let's look at case 2 now. Case 2, as you rightfully call it, we're looking at the cases where it ends with a 5. If the odd number ends with how many odd numbers are between here? 3, 5, 7. So there are 3 cases we have to look at. If it ends with a 5, that means the first number has to be 6 or 7 in order for it to be bigger than 500,000, because no number can be repeated. So this is 1, 2, 3, 4, 5, 6. So this number here is 5. So there's only one number going to go there, which is 5. Right here, so the number needs to be bigger than 500,000. So it has to start with either 6 or 7. So there are 2 numbers we can put here. After we take out them 2 numbers, they're left back with 4 number. 4, 3, 2, 1. So this will then be 2 times 4 times 3 times 2 times 1, which is equal to 2 times 4 times 3 times 2 times 1. That's 48. And then finally, as you call it, case 3. Case 3 is going to be the case where the number ends with a 7. So if the number ends with a 7, then we have case the number ends with a 7. If the number ends with a 7, then that means right here, so it can't be 7, it has to be 5 and 6. So the number ends with a 7 in this case. So there's only one way for that. Then it have to start with 5 or 6. So that is 2. And then this is going to be, how many numbers left back? 4, 3, 2, 1. So again, this is going to be 48. So add them here up and get the total possibilities. So the total ways we can get odd numbers greater than 500,000 without repeating digits is equal to 72 plus 48 plus 48. Add those up, 72 plus 48 plus 48, we get 168. That's the total possibility. Nice and easy, soft. All right. Now part D. Part D gives us a matrices question. And it says two matrices are given as A and B. By finding A times B, deduce that A inverse is 1 over 88 times B. So first thing we do is work out what's matrix A times matrix B. Matrix A times matrix B is going to be row by column. It's going to be 5 times 18 times minus 2 times minus 8 plus 3 times minus 6. You're going to get 88 here. So you're going to get 88. Without even working it out, I can see it's going to be 88, 0, 0, 0, 88, 0, 0, 0, 88. So what this works out to be is that A times B is equal to, if you factor out 88, you're getting 88 times the identity matrix. All right, nice and easy. Now, if you're to divide both sides by A, or rather, if you're to divide both sides by B, let's divide both sides by B. I know you can't necessarily divide matrices, but the principles remain the same. If you divide both sides by B, B over B cancel, and so you get A, that A is equal to 88 times, no, 1 over B is B to the minus 1. When you're multiplying it by the identity matrix, that doesn't change anything. You can just put I. And then what you get is flip it. If A is this, then 1 over A is equal to 1 over all of this. 1 over 88 times B to the minus 1. And so what we're getting is 1 over A is E to the minus 1, which is equal to 1 over B to the minus 1 is just B. So this becomes 1 over 88 times B. Nice. That's what we get. No, you didn't have to do it like that. It said deduce, it didn't say show. I deduced it. I deduced that by finding A times B, I deduced that A inverse is 1 over 88 times B. Now, you didn't have to do it this way. Let me put an or. An OR way would be OR. Why is it coming out like this? This is an OR. An OR is to do what they teach us to do. If you have A times B, A times B is equal to 88I. They tell us to pre-multiply the matrix by A inverse. So you pre-multiply by A inverse, and pre-multiplying by A inverse, you get B is equal to 88I times A inverse. That's one way. Or another way they tell you to do is pre-multiply by B inverse. Pre-multiply both sides by B inverse, and it works out. So you can pre-multiply by inverse as well. So this takes care of question 5. All right, it says now hence solve the system given as this for x, y, and z. When it says hence, meaning using this A inverse as 1 over 88 times B. So hence, without even looking too deep into the question, you know that x, y, z is going to be equal to 1 over 88 times the matrix B matrix B is given by matrix B is given by 18, 12 minus 1, 18, 12 minus 1, negative 8, 24, 20, minus 6 minus 4, 15. Multiplied by 7, 11 minus 6. All right. So when we multiply these two across, that will give us what x is, what y is, and what z is. That will give us our x, y, z. So multiplying them across, we're going to get this is equal to 1 over 88 times row by column. So you just put that in your calculator. 18 times 7 plus 12 times 11 plus minus 1 times minus 6. I get 264. 264. All right, and then you have minus 8 times 7 plus 24 times 11 plus 20 times minus 6. I get 88 here. And then finally, I have minus 6 times 7 minus 4 times 11 plus 15 times minus 6. That's minus 176. So in conclusion, x is going to be 264 divided by 88. So x is equal to 3. You're going to get y is equal to 1. X equal 3, y equal 1. and z equal -2. Nice and easy, soft. Nice. Now we go to the final question of the paper, question 6. Question 6 is typically going to be a differential equations question. And so we have this differential equation here. Differential equation, it says, a differential equation is given by y prime times cos x is equal to y sine x plus sine 2x. Show that the general solution of the differential equation is this. So to solve a differential equation, you want to put it in the form dy by dx plus k times y is equal to a function of x. So you have y prime. That's why writing back the question, we have y prime cos x is equal to y sine x plus sine 2x. And so I'm going to just bring over the y sine x to have y prime cos x minus y sine x, and that's equal to sine 2x. Okay, now once you reach this part now, you can divide through by cos x to get y prime minus, when you divide through by cos x, you get y prime minus sine over cos is tan, so you get minus y tan x. And that's equal to, you have to remember that sine 2x is 2 sine x cos x. So when you divide sine 2x by cos x, you get sine 2x. You get sine 2x. All right, so this is what we get. The reason for that is because, let me put a reminder up here, sine 2x is equal to 2 sine x cosine x. And so if you divide it by cos x, then you're really dividing 2 sine x by cos x. That's what you're doing. This is 2 sine x. So now we need to find the integrating factor I. The integrating factor I is equal to e times the integral of minus tan x. So it's integral of e, the integral of minus tan x. And the integral of minus tan x is going to be equal to e to the, when you integrate tan, you get ln sec. So it's going to be e to the minus ln sec, e to the minus ln sec x, which I can bring up this minus 1, and so e to the minus ln sec x is sec x to the minus 1. So that's the integrating factor, sec x to the minus 1. And so the general solution is just going to be y times your integrating factor. So it's y times sec x to the minus 1. But sec x to the minus 1 is cos x. So I'm going to write this as y cos x then. Sec x to the minus 1 is cos x. We put it there. Sec x to the minus 1 is cos x. So that means I have y cos x. Y cos x is equal to the integral of 2 sine x times cos x, but 2 sine x times cos x is just going to be sine 2x. So it's equal to the integral of sine 2x dx. Nice and easy. So when you integrate sine 2x, you integrate sine 2x. When you differentiate sine, you get cos. So when you integrate sine, you get minus cos 2x over 2 plus some constant c, and that is y cos x. All right, so now we have y cos x. Now we need to show that the general solution of the differential equation is y equal to a half sec x minus cos x plus c sec x. So we need to get rid of this cos 2x over 2. And better I put my plus constant as maybe a plus c. Since they're using c, put a plus c. Plus c. So I divide through by cosine. Dividing through by cosine, I'm going to get y is equal to minus cos 2x over 2 over cosine. Now minus cos 2x is the same as 1 minus 2 cos square x. 1 minus 2 cos square x being divided by 2 cos x. Then we have the c over cos x, but plus c over cos x. So divide through by cos x, that's what we get. C over cos x, so this is y. Now after you do that division, always remember you can separate the part in the numerator as two separate fractions. So this is 1 over 2 cos x. So y is equal to 1 over 2 cos x minus 2 cos square x over 2 cos x. 2 over 2 cancel, so you just get minus cos x plus c over cos x. Now, y is equal to a half of 1 over cos x. Now 1 over cos x is sec. This works out to be a half sec x. A half sec x minus cos x. And then c over cos x is c sec x. C sec x. Nice and easy, soft. Make this look more like a C. This look like C sec. This look like C sec. So put C. Show that this is a constant. This look like C sec x. C sec x. So there we have it. We prove it. Nice and easy, soft. Now the second part says hence or otherwise solve the initial value problem. Y naught equals 0. Meaning when x is 0, we're going to get that. When x is 0, y is 0. So solve the problem. So solving this problem, when y is 0, x is 0. So 0 is equal to, when you put cos, the cos of 0 is, the cosine of 0 is 1. So this becomes a half. So 0 is equal to a half. Cos of 0 is 1, so that becomes minus 1. Plus cos of 0 is 1, so that becomes plus c. So now we'll make c the subject, which implies a half minus 1 is minus a half, so c equal a half. C equal a half. So the solution to the initial problem then is y is equal to a half sec x minus cosine x plus c sec x, and c is a half, plus a half sec x. This is how we do this question, plus a half sec x. Nice and easy, soft. Now, it says, oh, so we finished this part of the question, soft. So now we go to part B. Part B says, a differential equation is given by y double prime plus 2y prime plus y equal x e to the minus x. Determine the solution of the complementary function. So the solution of the complementary function of this equation, we're going to call y double prime u squared. So we have u squared plus 2u plus 1 equals 0. Now this is known as the auxiliary equation. So we solve the auxiliary equation for the solution of the complementary function. So we can factorize this to get, this is really u plus 1 all square is equal to 0. And so what we're getting is u is equal to minus 1 repeated. U is equal to minus 1 repeated. Now since u is equal to minus 1 repeated, then therefore the solution of the complementary function is going to be, the complementary function is given by, I like to call it yc, and yc is equal to some constant, you can call it, so it's a plus, all right, let me write it better. Let me write it how we're used to seeing it. So it's going to be e to the solution times x, so it's e to the minus x into p plus qx. That's the standard form. This is how most of us will be used to seeing it. I was just about to write it as p e to the minus, I was just about to write it as p e to the minus x plus qx e to the minus x, but I'm saying I can't start out like that. This would be the solution of the complementary function. Moving right along, it says, given that the particular integral is this, then determine the general solution of the differential equation. So first thing, give us the particular integral. So it gives us that yp is equal to, yp is a killer, it's ax cubed plus bx squared ax cubed plus bx squared times e to the minus x. So what we're going to do then is find out yp prime. To find yp prime, we're going to use product rule to differentiate this. So we keep the first. So we write back our ax cubed plus our bx squared. So we keep the first. Then we multiply it by the derivative of the second. When we differentiate e to the minus x, we get minus e to the minus x plus, we keep the second, which is e to the minus x, multiplied by the derivative of the first. The derivative of the first is 3ax squared plus 2bx. Nice. All right. So what we get is yp prime is simplified to be equal to, I don't even need to simplify that. I'm just going to find yp double prime. To find yp double prime now, we're going to differentiate yp prime. And so we keep the first. So we're going to get ax cubed plus bx squared keep the first, then we differentiate the second. We differentiate minus e to the minus x, we're going to get minus and minus give us plus, so we get e to the minus x plus, we keep the second, which is minus e to the minus x, keep the second times the derivative of the first, and the derivative of the first is 3ax squared plus 2bx. All right, now we need to differentiate this one now, plus keep the first, which is e to the minus x, times the derivative of the second. We differentiate 3ax squared, we're going to get 6ax. So we get 6ax plus, when you differentiate 2bx, you just get 2b plus, keep the second now, which is 3ax squared, plus keep the second, times the derivative of the first. So you get 3ax squared plus 2bx times, of course, times the, so we keep the first, differentiate the second, plus keep the second, differentiate the first. Differentiating the first is timesing it now by minus e to the minus x. So now we're good and we're all set to go. Now all we're going to do is go back around here, and we're going to remember that we have y double prime plus 2y prime plus y is equal to x e to the minus x. That's the equation we will use to solve for a and b. Y double prime plus 2y prime plus y, that's equal to x e to the minus x. And so this takes a lot of concentration. So what I want you to do is, we need 2y prime, so multiply this by 2. You're going to multiply this by 2, you can put a 2 out here and a 2 right here. All right. Now what I want you to do is add up. You're going to have to add these. Yp plus 2yp plus yp prime. If we're going to add them, let's go about doing that. This is really 2ax cubed plus bx squared. So I have 2 of this. I'm going to underline the like ones. I have 2 of this. I have 1 of it here. I have 1 of it here. What does that mean? Ax cubed this plus ax cubed this minus this, those cancel, that becomes 0. That becomes 0. Right? So that becomes 0. I'm just adding all of these 3 now. Adding them. All right? So those become 0. Next now, I'm going to add, because I'm now adding, cancel out those 1. Now I'm going to add with ax squared now. So I have 2e to the plus 3ax squared. I have 2 of this. I have another 1 of this right here. Do I have any more of them? I have one more of it right here. All right, so now you have 2e to the minus x plus minus e to the minus x. 2 plus minus this is 1, plus minus this, that cancels, so that becomes 0 as well. That part becomes 0, so what am I left with? I am left with now, I'm just left with, yeah man, we're nice now, because we just left back with this part. Just left back with this part. Yeah man. So we can just put, let's do it around here. So that implies what we're left back with is this part, e to the minus x, 6ax plus 2b, e to the minus x into 6 into 6 what? 6ax plus 2b what we're getting is that this is now equal to xe to the minus x. So we can use this now to solve for a and b. So using this to solve for a and b, we're going to get that. This is really saying 6ax e to the minus x plus 2b e to the minus x. That's equal to x e to the minus x. So what does that mean? That means that 6a is equal to 1. That means that 6a is equal to 1. So that means that a is 1 over 6. And there's no other e term over here, because this part equals this, and so 2b must equal 0, and so b equals 0. B is equal to 0. Nice. Now that we find b and we find a, we know that the general solution y is equal to the complementary function plus the particular integral solution. So it's yc plus yp. Now the complementary function we found, it was e to the minus x, e to the minus x into, what did we use again? P plus qx. I want to be consistent. P plus qx. And then it add plus yp, this particular integral, but they told us yp was ax cubed plus bx squared e to the minus x. Now b is 0, and so it is just a, which is 1 over 6 x cubed e to the minus x. So it's just plus 1 over 6 x cubed e to the minus x. Nice and easy, soft. So this is 2018, very easy paper, one of the easiest years of CAPE. Really hope this was helpful. Make sure to subscribe, and all the best prepping for your exam.